Alright guys, this is our next video in our Kinematics series where we're going to talk about vectors. Now that word will elicit a couple of things in your mind. If you've never really dealt with vectors before, you're going to think more like that.
Vector! That's me.
And if you've taken Calc 3 Diffie Q, you'll probably instead think like,
Oh, poop.
But really, honestly, you should be thinking more like this.
Destroy it!
And then I'm going to go. No. Alright, roll the intro.
Do you feel the vibes?
Now I know what you're thinking. You're thinking, I saw Despicable Me. I know that a vector is just a
Quantity represented by an arrow with both direction and magnitude.
And you'd be right. So why all the doom and gloom? Why all the huff and puff? Why do I keep going on about how you're going to hate this? Well, it all boils down to trigonometry. That's right. Vectors are quantities represented by an arrow that have both direction and magnitude. But that means that we have to treat them differently from how we treat other quantities. So you might have a vector going this way, and then another one going this way. And the result of that vector, when you add those two things together, we'll talk about adding vectors in a minute, is this, which makes, you guessed it, a triangle. Oh yeah. But I'm jumping ahead of myself a little bit. Before we deal with all the triangles and we deal with all this stuff, let's talk about what a vector really represents, right? So we have our original kinematic variables, right? Position, velocity, and acceleration. And honestly, these are all vectors. Yeah, I sort of lied to you at the beginning and treated them like normal quantities. But if you remember from our example from part 2, we talked about how acceleration was negative and in the opposite direction of the velocity. This is what we mean when we're talking about direction. So if you're going, let's say, left and right, this direction might be negative and this direction might be positive. And that works really, really well for one-dimensional kinematics. You barely even have to consider them to be directions. But when we talk about multiple directions, like what happens if now we start talking about a coordinate plane and we deal with a y-axis, and then we have a vx, an ax, a vy, and an ay, well, these are what we really have to deal with. We'll have something going up and down and something going left and right. And if you notice in my example, I do have something going up and down and something going left and right where we create the triangle. So when we look at our quantities now, instead of x being something that is just positive or negative, positive x indicates something that's going to the right. Negative x indicates something going to the left. A positive y indicates something going up, and a negative y indicates something going down. This applies too for velocity and acceleration. If I have a positive acceleration in the x direction, then the thing is speeding up going to the right, or slowing down going to the left, right? Because the acceleration is the change in the velocity. So if I have a velocity that's positive and an acceleration that is negative, this is decelerating. But likewise, if I have a velocity that is negative and an acceleration that is positive, this is also decelerating, but in the negative direction. So you can see now that this is how we're going to deal with our vector quantities. Let's start with our position instead, before we get too complicated. So if I have a position vector, let's say I'm on a street, and I want to go 3 blocks to the right, and then I go 4 blocks up. Well, how many blocks am I from home? Well, I can figure that out by finding what's called the resultant vector, which is just the two vectors added together. So we'll call this 3 vector and 4 vector. So 3 vector plus 4 vector actually creates a triangle. So this is not equal to 7. It is instead equal to the Pythagorean theorem for this particular triangle. So we'll get a squared plus b squared equals c squared. This is the Pythagorean theorem for a triangle. So I would instead put 3 into this a spot, 3 squared, plus b squared. This will be 4 squared. And this will equal my resultant squared, so c squared. 3 squared is 9 plus 16. This is 25. So 25 is my c squared, and that means that c is 5. So even though I went 3 blocks and then I went 4 blocks, I'm actually only 5 blocks, as the crow flies, as one would say, from home. Something interesting about this too is that we can consider our 3 vector and 4 vector to be what are called the components of our vector as far as we are from home. So this would be our total vector, 5, and 3 and 4 lie along the x-axis and the y-axis, and this would make what's called a component form. So y is one component and x is another component. So we can get that our 5 vector is equal to 3x hat plus 4y hat. Or for those of you from Calc 3, you can use IJK form. It's a little bit more nuanced, but it's not really that important, where we get 3i plus 4j. So this is what we call component form. Notice that we can get the 5 vector from the 3 and 4. The x and y are just telling us along what coordinate axis that number falls. The hat here just means direction. We can break any vector up into its component form if we want to. So let's scroll down and make a similar thing. We're going to have a coordinate plane here with x and y. So here will be my x, here will be my y. And if I have my 5 vector this way, I can break it up into its components along the x. So I'll have a 3x and a 4y. Now, that means that there's some angle in here. We'll call that theta. This is where the trigonometry part comes in, and we can use what's called SOHCAHTOA. SOHCAHTOA, I write it this way for a very specific reason, just tells us that the sine of the angle theta is equal to the opposite side, which would be our 4, divided by hypotenuse, which would be 5. The cosine of that angle, theta, is equal to the adjacent side, which is 3, divided by the hypotenuse, which is 5. And the tangent of angle theta is equal to the opposite, which is 4, divided by the adjacent, which is 3. So this is how we can use SOHCAHTOA to figure out our angle. Likewise, if we know our angle but don't know some of our components, we could also use this SOHCAHTOA to figure that out. So in this case, when I'm looking for my angle, I could figure out that the inverse sine of 4 over 5, for example, we could use any of these 3, is 53.1 degrees. And that would give me my theta in this case. That means that my overall vector, my 5 vector, would have 5 units as the magnitude, which is just the value of the vector, at 53.1 degrees from the horizontal. And that would be the direction. So there we go. So that's for one single vector. But now let's imagine we have 2 vectors, both in the x and y directions. So let's look at a couple of vectors. Our first one is going to be 5, 3. And this is just going to be an x and y. And we're going to add that to another vector that is 1, 6. Now, what we do in that case is we would add only the x components. So we would get the vector 6, 9. And this would be our resultant vector for this. Now, if I wanted to find the magnitude of this new vector, I would have to use these components in the Pythagorean theorem to figure out the magnitude and the angle. Likewise, I could have been given something with a magnitude and a direction, and I would have to break that up into its component form in order to get this 5, 3, and 1, 6. So you can see how, yeah.
Boy, that escalated quickly.
As always, don't forget to like, comment, subscribe on this video so that my students can see it. I mean, you know, they still won't watch it, but it's fine. Make sure that you like, comment, subscribe. We'll talk more about multiplying vectors and stuff in the future when we have to deal with that and it becomes relevant. As always, appreciate it.